All right, for this last bit in chapter 12, and this is not that long at all. There's one little piece hanging off of the tree here, and it's tying together equilibrium, the scourge of humanity, with thermodynamics, the stuff that we've been dealing with thus far. And it's really just a couple of equations that tie the two together. Just the relationship that if we have a defined state of equilibrium where we have a known K value, we can determine the free energy of that state based upon the value of the equilibrium constant. And that is that delta G is equal to negative R, R being the thermodynamic gas constant, 8.314 joules per mole Kelvin, multiplied by the temperature in Kelvin, multiplied by the natural log of the equilibrium constant K, and that would give us our delta G value. Now, knowing what we know about what K says in terms of position, we can kind of naturally get a feel for what it's going to say. If K is greater than 1, delta G is going to be negative. And that should make sense. A K greater than 1 indicates a product favored reaction. And if the reaction is product favored, then the forward reaction that makes the products would be spontaneous. The two speak the same language. And consequently, if it were the opposite, if K is less than 1, then delta G would be positive. Because again, think of the implications. A K less than 1 indicates something reactant favored. If the material is reactant favored, then the forward reaction wouldn't be spontaneous. It would be non-spontaneous. The reverse reaction would be spontaneous. So when we start thinking about things in terms of those values, then we can still say, okay, they're talking the same language here. Our Ka values for weak acids are non-spontaneous in the forward direction. We get some product, but the majority of it stays as reactant. Now that's if we're at standard conditions. If we are not at standard conditions, or if we are not at equilibrium, then the equation changes. And it changes to delta G, the non-standard version, is equal to delta G, the standard version, plus this adjustment for the lack of equilibrium, where we use the value Q, the reaction quotient, instead of the equilibrium constant K. Go ahead. Yeah. So what this second equation allows us to do is it allows us to look at a reversible system, not at equilibrium, and predict the spontaneity of that system. So if we manipulate the system by flooding it with extra reactants, according to Le Chatelier's principle, does that yield a more favorable spontaneity value? And so that's what this second equation allows us to do. It allows us to solve those kinds of problems, which are related to equilibrium, but not exactly equilibrium, and give us a way to adjust those kinds of values to figure out, okay, we did this. Does that actually change the spontaneity of the forward reaction? And honestly, we'll do a lot more with that kind of manipulation as we get into tomorrow and Friday, talking about electrochemistry, because a lot of electrochemical systems, which again, electrochemistry is just an application of thermodynamics to redox reactions. But what we'll see is that there are some ways that we can generate extra voltage by manipulating the equilibrium inside of the battery. And the calculation that we can do to figure out how much extra voltage we get is an application of that delta G reaction that we saw just a second ago. So let's take a look at a practice problem. We've got a familiar equilibrium system here. The interconversion between nitrogen dioxide and its dimer, dinitrogen tetroxide. What we want to do is we want to determine the value of delta G at 298 Kelvin. And we also want to determine the value of delta G if we have partial pressure values that put us not at equilibrium. So for the first part here, if we had an equilibrium constant K, then we would just be able to plug it into that delta G is equal to negative RT natural log of K. Without that, we're going to be stuck using formation values and calculating delta H and delta S kind of the, for lack of a better term, the traditional way. Using the formation values, using the standard molar entropies. So I flip ahead to the nitrogen section in my text, and I see that for dinitrogen tetroxide, N2O4 gas, delta H is 9.2. And nitrogen dioxide, NO2 gas, is 33.2. So delta H is equal to 9.2 minus 2 times 33.2, which would give us negative 57.2 kilojoules. And for entropy, N2O4 in the gas phase is 304 joules per Kelvin. And nitrogen dioxide in the gas phase is 240 joules per Kelvin. So 304 minus 2 times 240 would give us negative 176 joules per Kelvin. So to figure out delta G naught, that is the standard delta G, it would be delta H at standard conditions minus T delta S at standard conditions. So negative 57.2 kilojoules minus 298 Kelvin times negative 0.176 kilojoules per Kelvin Again, we need to convert the joules into kilojoules so that we don't have a unit mismatch here. The product of these two is 52.4 kilojoules. So delta G is going to be negative 4.8 kilojoules. So that's part one here. Part one, just kind of your standard figure out delta G, especially since we weren't given an equilibrium constant at this particular temperature. Again, if you're not given that, go revert back to what you know how to do. 52.4. Now for the second calculation, we're going to need to use that other form. Delta G is equal to standard delta G plus RT natural log of Q. We have our delta G at standard conditions. It's negative 4.8 kilojoules. R is 8.314 joules per Kelvin, mole Kelvin. So we'll have to switch that to kilojoules as well. 0.008314 kilojoules per mole Kelvin. Let's assume that we're still at 298 Kelvin, even though it has not been said otherwise one way or the other. And for Q, remember, Q is calculated the same as the equilibrium constant. It's the ratio of the pressures of the products divided by the pressures of the reactants here, since we're given pressure values. If we were given concentration values, it'd be concentration of products over concentration of reactants. So N2O4 is 1.60 atmospheres. NO2 is 0.40 atmospheres, and that is quantity squared because we have a coefficient of 2 in the equilibrium. So hard as it is to go back, we can't forget the fundamentals of equilibrium. When we do products over reactants, we got to make sure that those coefficients come along for the ride as the exponents. We can't forget that part. So putting all of that together, 1.6 divided by 0.4 squared gives us a natural log here of, this is 10. Natural log of 10 is 2.30 times 298 times 0.008314. So we have negative 4.8 kilojoules. Our adjustment for this non-equilibrium condition is 5.70 kilojoules. So delta G under these conditions is a positive 0.9 kilojoules. So we can see that by flooding this equilibrium with a whole bunch of extra product, we have turned a spontaneous reaction at 298 Kelvin into a non-spontaneous reaction at that same temperature. Now, what does that really tell us? That tells us that Le Chatelier's principle is going to take over. It's going to shift the whole thing back toward the reactants until we get back to equilibrium. And at that point, delta G will be 0 because we are at a reversible equilibrium condition. So really all we're doing is we're just kind of stitching together the first half of the course and this part of the course. Any questions with this example? Okay. So we want to look at this problem here. Considering the decomposition of barium carbonate, what is the equilibrium pressure of carbon dioxide at 298 Kelvin and at 1100 Kelvin? Now, the one thing that we want to consider is that given this reaction set, the barium oxide is a solid, not in the equilibrium constant. The barium carbonate is a solid, not in the equilibrium constant. So if we find the value of the equilibrium constant K, that would stand in for either the concentration of the carbon dioxide, or in our case, what we're looking for, the pressure of the carbon dioxide. It would be the same either way. So if we use our equation here, this will give us the value of K. But we're going to have to find the delta G first from the formation values. So there's two parts to this question. All right, go ahead and think on that. Work on that a little bit. We'll come back in a few minutes and review it. And that's the last problem in the chapter. All right, so the key to this problem, there's a lot of ways that you can do this. And I think that's one of the comforting yet frustrating things about these kinds of thermodynamic calculations is that there are a lot of ways to get to the same place. So even if you don't do it the way that I did, that doesn't necessarily mean that you did it wrong. So this is the equation that we are striving for. We need to know what delta G is, though. And so to do that, we're going to have to figure out what delta G is from these formational values. And so Some of you went and did the delta H of formation, delta S calculations, put it into that Gibbs equation to figure out delta G, and that works. That works if we're at 298 Kelvin in particular. Now, if we're not, then there are adjustments that we would have to make. So to get delta G at standard conditions, because that's what this is ultimately asking us for, we are going to need the products. So negative 528.4 kilojoules plus negative 394 kilojoules minus the reactant, negative 1138 kilojoules. And if we do that, we would get a standard delta G value of negative 528.4 plus negative 394 minus negative 1138, positive 215.6, which if we round to the ones place would give us a positive 216 kilojoules. Now, if we take it from here, now we use that other equation, delta G standard is equal to negative RT, natural log of K. We've got 216 kilojoules is equal to negative R, which we're going to have to convert 0.008314 kilojoules per mole Kelvin times 298 Kelvin times the natural log of K. And if we carry that out further, 216 divided by negative 0.008314 divided by 298, we get negative 87.2 as the natural log of K. So E to both sides of that would give us a K value of 1.4 times 10 to the negative 38th. Now to do the 1100, same calculation, because delta G at standard conditions would still be 216 kilojoules. This time it's 1100 Kelvin instead of 298. And so this time we would get only negative 23.6 as the natural log of Kelvin, or natural log of K, which would give us a K value of 5.5 times 10 to the negative 11th. Now, what we'll notice is that these calculations are going to have some wavering kinds of, we're making a pretty big assumption. We're making a pretty big assumption that the standard free energy change is going to be consistent, that it's going to be unchanging with drastic changes of temperature. We make the same kind of fundamental assumptions with delta H and delta S. And we know that within a little bit of reason, especially delta S, is going to have a lot more variability with temperature, which means delta G would have variability with temperature as well. So the reason I bring this up is this decomposition reaction between barium carbonate and its decomposing counterparts is one we can do. You can take barium carbonate, put it in a flask, heat it up on your Bunsen burner, and it will generate enough carbon dioxide to put out a flame. Now, if you take a burning wood splint and put it over the mouth of the flask, the carbon dioxide would basically extinguish it. So we know that this is kind of distorted, but based on the information that we have, based on the way that we're using these equations, that's what we're going to have to go with. So would I expect that, since remember that these K values are actually pressures, so we're talking about 1.4 times 10 to the negative 38th atmospheres of carbon dioxide at room temperature, 5.5 times 10 to the negative 11th atmospheres at 1100 Kelvin, I think we'd be pretty safe to assume that they're actually going to be better than that. But again, we're going to work within what we have here. Any questions about this problem? All right, congratulations. We have finished another chapter, which puts us at just 2 to go. So we will start the first of those 2 tomorrow, looking at electrochemistry. And then we'll finish up next week with just a brief look at solid state chemistry, just enough to kind of satisfy what we need to know for the ACS exam. And then we're in review mode. So go ahead and hit the stoplight question on the way out and enjoy your lunch.